Hi, my name's Chris. I'm a master's student in a data science program, and today I'm going to teach you guys about K-means. To follow along in this video, you'll need some knowledge of programming. I've done everything in Python. You should have some knowledge of data structures and algorithms, and you should have some knowledge of linear algebra as well. Okay, what is K-means? K-means is a clustering algorithm. A clustering algorithm is different from what I talked about in my last video, which is KNN, which is a classification algorithm. A clustering algorithm looks at some data and it groups similar kinds of data into different clusters. It doesn't need to know anything about the data, it just looks at the different features of the data and groups it by similar features. This differs from a classification algorithm where it does need some information about the data and which classes of data exist already. But with clustering, we can just say, okay, I want to separate this into 4 distinct groups. Find me the 4 most distinct groups of data within this data set. An example of this is if we had a data set of pictures of nature, and we want to separate it into 4 different clusters, each one representing a different season. So summer, winter, fall, spring. What the clustering algorithm would do is it would then look at each picture and try to find differences in the pictures. For example, it might pick on color. Pictures of winter are probably white for all the snow. Pictures of summer are probably green and yellow because the sun's shining. Pictures of autumn are orange because of the leaves, and so on. And so it would just separate it into 4 different groups. It doesn't need to know that they're actually representing seasons. It just sees, okay, there's similar colors here, so they're all part of the same set. These ones are also similar colors. That's how a clustering algorithm works. Okay, I'm going to switch over here to some code, which is going to represent some data that we are going to work with. This here is just to generate clusters of data to represent the data set that we'll be working with in a second. This just generates a bunch of XY pairs, so we're working in 2 dimensions here, and this just plots it. One with color to separate the different clusters, and one without. So first, for example, is if I have a data set that looks like this, I can see personally that there's 2 very distinct clusters here. These are separated by a very clear boundary in the center, where all the points on the left probably belong to one cluster and all the points on the right belong to another. So a clustering algorithm, a good clustering algorithm, will separate it into 2 different clusters like so. We can do this with any number of clusters. So in this example here, we have 4 separate groups, kind of like the 4 corners of a square here. And again, we can very clearly see the boundary. And if I run a good clustering algorithm on it, it will end up looking something like this. Finally, for our last example, we could have a clustering algorithm that looks at data like this. And this data could be hard to separate from each other. You could just draw a big X through it, and that could separate it into 4 different groups. But a good clustering algorithm will, for example, separate it into 4 groups, like so. You could separate it into 2 groups as well, or 3 if you really wanted to, and those would all look different. So what our actual clustering algorithm looks like, again, we have our generate function, which just generates XY pairs, and I've written a transpose function as well, which is used for making it easier to work with in PyPlot. When I run this, it generates, like I said, XY pairs, all between, and if it just, with these 2 zeros, these are my X and Y offsets, plus my density, or multiplied by my density, I should say. And so that means that everything is between 0 and 1. If I run it again, giving an offset of 1 and multiplying everything by 2, I end up with data that looks like this. So that's how the generate function works. I can plot the data that I've just generated here, and like I said, everything between 1 and 3, there it is. So the data that I'm going to work with for K-means, I have 4 clusters, 50 points per cluster, and I'm going to group them into one big list. And what we want is something that looks like this when our clustering algorithm has finished running. But when it starts, it's going to look like this because there's no differences in the labels yet. I've also written a function to calculate the Euclidean distance between each point, and we're going to need this for calculating the distance between each point and what's called a centroid. I should probably get into what KMeans actually does and how it works. What KMeans does is it looks at what's called a centroid, and the centroid is the center of a cluster. So in our 4 clusters here, our centroids would be in the center. So our green centroid would be right there, our yellow one would be there, our red one would be there, and our blue one would be there. But how does it get to that point? Well, at first, our centroids could be generated randomly, so they could be anywhere on this plane. Once we have our centroids, we find the distance from each point to each centroid. And then we separate them into groups based on which centroid is close, or which point is closest to each centroid, and those become our clusters. We then take a look at the clusters, and we find the center of them, and that becomes our new centroid. So then we repeat the algorithm until it converges, so the centroids and clusters stop changing. Okay. So let's actually go through the code. In our KMeans function, we have 3 arguments, k, n, and l. K is the number of clusters we want, n is the number of iterations, and l is our data. This function to generate initial centroids, there's many ways to do it, but in this case I've just generated them randomly. They're all points between 0 and 5 on both the x and y axis. And then we're going to run it n times. Usually you would run it until convergence, so until the centroids stop changing, but this is for the sake of just showing how the code works a little bit easier. Okay, so that's why we do for I in range, so it runs n times. The first step is creating an empty list of labels, and we're going to, for each item in this list is going to represent that index, the point of that index, so is closest to which centroid. So what I mean by that is the first element of the list corresponds to our first data point, and it would, if it was 1, we're saying it's closest to centroid 1. If it's 3, it's closest to centroid 3, and so on. To do that, I've written a little bit of code that calculates the distance from each centroid, and then it sorts that list from shortest distance to longest, and it returns the centroid closest to that point. Then we append that to our list of labels. So that's what gives us our clusters. This PLT stuff is just optional for showing what it looks like. We've then generated a list of new centroids, which is empty for now, and we'll fix it, or we'll generate the elements for that down below. I've got another index value as well. It's called label. I'm sure there's a better way to do this, but that's okay. And then for each centroid, what we're going to do is we're going to look at each point and see if that point belongs to the centroid or not. So for each point, if in each point it is closest to that centroid, then it belongs to the cluster, and we'll add it to the cluster, and then we'll plot each cluster. And then we will find the center of the new cluster, and that becomes our new centroid. And then we show everything, and then we replace our centroids like so. Okay, so let's actually run it and see what it looks like. Oops. At first we have our randomly generated centroids. We have 4 of them, 1, 2, 3, 4. And we can see all the yellow points are closest to this one, all the blue points are closest to this one, green one's here, and this poor centroid here has no points closest to it. So the next step, we calculate the center of this cluster, the center of this one, and this one here, which has no points, so it doesn't change. but this one should move down there, this one should move over here, and this one should move down there somewhere. And that's what it does. Great. We have this centroid here with all the blue points in its cluster, this centroid here with all the yellow points in its cluster, this green one with all the green points here, and this one has got a few points now as well. And then they update again, and we can see in this cluster the centroid has moved, it's actually stayed the same, I think. The red one has changed where it's now closest, all the red points, their centroid has moved down a bit. The same with the green ones, it's moved closer to that cluster, and all the yellow ones, it's moved closer to that cluster. And then we do it again, and we end up with this. And this is what we were looking for. These centroids are in the center of each very distinct cluster. So if we run it again, it doesn't change. So this is what we would call convergence. I'm going to run this with another example. I've changed our data a little bit, and it's going to be very messy. We look at something like this. So there's no very clear decision boundaries here, unfortunately. But we can still run K-means on it. When I do this, I run it 10 times, excuse me. And we end up with, okay, so 4 randomly generated points and all the closest points to it. And it updates. This moves closer up, 2, 3, closer up. And then we recompute and we see this guy has accumulated 1 point over here, but these really don't change a whole lot. This moves closer up and takes up more points. So the centroid shifts again. These guys move away a little bit because they're losing points. And this cluster gets bigger and bigger until eventually we have 4 distinct clusters that don't change. And that is how K-means works. Okay, that's it. If you have any questions, please let me know, and I'll see you guys in the next video.